Hi there and welcome back to Tripplikit and to part 4 of the digital synthesis tutorial. And in this video we're going to build an oscillator. At least we're going to build most of an oscillator. I think the oscillator video is going to run into a second video because of the amount of material we have to get through. Firstly, just the usual proviso that the audio effects in these examples in this video are quite subtle and are generally lost somewhere in YouTube's processing. So if you look in the description, there will be a link to where you can download .wav files and listen to them as they were intended. Also there'll be a link to any bits of code I'm generating in the course of this tutorial. Okay, first a quick recap. Although they're conventionally called oscillators, the waveform generators in the mean green are actually going to be using single cycle samples and playing samples back. This method of sound generation was chosen because playing samples back is something that digital audio systems do very efficiently. Since we know exactly what's in our samples, we can accurately assess the noise we're going to produce by playing them back. We can also make sure that whatever pitch we play our samples at, we can be sure that none of the harmonics are going to exceed the Nyquist frequency and generate yet more noise. The aim with the mean green is to develop a traditional analog type synthesizer. So we're aiming to have a sawtooth wave and a square stroke pulse wave. And initially we're going to look at the sawtooth wave, and I will return to the square stroke pulse wave anon. Okay, so we want to generate a single cycle sample or wavetable for our sawtooth waveform. We do this using Fourier synthesis. Now I don't intend to go into the mathematics of this. If you're interested, there are loads of resources on the web. I'm just going to give you the end result. Okay, to generate a sawtooth waveform by Fourier synthesis, we use the following equation. We take the first harmonic, add to it half the second harmonic, and a third of the third harmonic, and a quarter of the fourth harmonic, a fifth of the fifth harmonic, a sixth of the sixth harmonic, a seventh of the seventh harmonic, an eighth of the eighth harmonic, a ninth of the ninth harmonic, and a tenth of the tenth harmonic, etc. You can see it looking more and more like a sawtooth wave as we add harmonics. Our theoretical sawtooth wave has an instantaneous transition on the edge of each tooth, and to reproduce this we would need to keep on adding harmonics to infinity. As you might expect, a wavetable of finite size can't contain an infinite number of harmonics, so how many harmonics can it contain? Let us consider a wavetable of 64 samples. The first harmonic or base frequency is 64 samples per cycle, the whole of the wavetable. The second harmonic is twice the base frequency, so half the wavelength, at 32 samples per cycle. The fourth harmonic, and I'm not going to go through them all, is 4 times the base frequency, so a quarter wavelength, so 16 samples per cycle. The eighth harmonic is 8 times the base frequency, so an eighth the wavelength at 8 samples. The 16th harmonic is 16 times the base frequency, so 16th the wavelength at 4 samples per cycle. The 32nd harmonic is 32 times the base frequency, so a 32nd of the wavelength at 2 samples per cycle. But wait, where's the waveform gone?
Well, here it is, or one cycle of it hand drawn in. You can see that the value of the waveform is 0 at the sample points, so that's no good. Indeed, if we look back at the 16th harmonic, that triangle wave is what our interpolation algorithm is going to give us, not the sine wave we want. The result will be digital noise. We'll find out just how much this noise is in a minute. There is also a maximum base frequency we can use a wavetable for. Here we have a wavetable containing 16 harmonics. We are using it to generate a sawtooth wave starting at a base frequency of 500 Hz and increasing the frequency to 1500 Hz. At 1500 Hz, the frequency of the highest harmonic has reached the Nyquist frequency at 24 kHz. If we try to use this wavetable to generate a sawtooth wave of a higher frequency than this, the harmonics will exceed the Nyquist frequency and we will be introducing digital noise.
Okay, so we know how to generate our wavetables. Now we need to know how many wavetables we need, how big those wavetables need to be, and how many harmonics they should contain. We'll look at this last one first. Let's first consider when and how we select a wavetable. The important factor here is how many harmonics the wavetables include. The more the better, so we get the best possible high frequency performance out of the oscillator. And we don't want to change wavetables while we're playing a note, because this could change the output level suddenly from the oscillator and hence create a click. So we want to select a wavetable when a note starts and stick with that wavetable the whole time the note is playing. What we do is pick a wavetable where the maximum harmonic is 1 octave below the Nyquist frequency for the frequency of the note we're starting. This octave gives us 1 octave headroom for pitch bend and pitch modulation.
So, for example, let us say our note is Concert A, or 440 Hz, which is MIDI note 69. The frequency of the table's maximum harmonic should be no more than 12 kHz. Thus the maximum harmonic included in our table should be 27, given that 12,000 over 440 is 27.27. Now let's think about how many wavetables we need. I first developed this system on the Red Sound Darkstar. Originally I had one table for octave because, in those days, the memory available on microcontrollers was very limited. This meant that in the above example this table would be used right down to the note number 58. The next table down being used at note 57. This would have 1200 over 220 or 54 harmonics, which is considerably more. In this case we found that there was a notable change in timbre between notes 57 and 58 using this method, and the human ear is just too good at picking that kind of thing up. In the end, in the Darkstar we compromised and managed to squeeze in 3 tables per octave, but in the mean green I would really like to use 1 table per semitone. Which brings us to table size. We've already found that the theoretical maximum harmonic number is half the table size, i.e. for a 64 sample table the maximum harmonic number is 32. However, we have also noted that the very highest harmonics are somewhat suspect. As we found for sine waves, the bigger the wavetable the lower noise. If we were creating a soft synth, then we just generate lots of huge great big tables. After all, a megabyte is nothing on a PC. However, our STM32 only has 512 kilobytes of ROM, and I know I have no idea at this stage how much is available for wavetables. So I think at this point the best thing we can do is generate some wavetables and see how they perform, so we can get a better idea of what we actually require. Okay, before we get into looking at any code, I have written a PC application called Mean Green PC Dev, which I can use to test out all the software algorithms on the PC, which is an awful lot easier because you can step through code. We can save outputs to files. This is driven from little text files which tell it what to do when. I will go into the format of these once we get to use it in a bit more detail, so we can absolutely reproduce what we're doing. It just makes debugging a whole load easier. Now in the final Mean Green, the wavetables for the oscillator will be stored in flash memory and uploaded with the code. However, in the dev version, the PC dev version, they are calculated when the program starts up. What's more, when they are calculated, the results are saved to a .h file which looks something like that, and that is included in the hardware code. So as you can see, we just have a constant int 16 and then a big table. Okay, so this is sort of the proper first Mean Green code we've written. However, it only exists in the PC version. So shall we go through this quickly? This is Wavetable Generate Table, it's called. It takes the number of harmonics, it takes a pointer to where the table should be written, and it takes a wavetable size. Now the wavetable is just in one big table. If we look back in here, there is absolutely miles and miles of that, which has several tables in, and then it just has a list of start points. It's easier than having lots of tables, separate tables defined. So that's what the table data start is. Okay, so here we count for each sample, that's each point in the wavetable. We have a sample val, which is used to sum up the value that's going in the table, and then for each harmonic here we calculate a phase, which is from 0 to 1 is one cycle of the sine wave in the phase variable, so it's the sample times the harmonic over the wavetable size. Okay, the f mod here just makes the phase between 0 and 1, so if it's 2.5 then that line will make it into 0.5. That's because the sine function can be inaccurate for very high values, but it's very accurate between 0 and 1 cycle. So we add to our sample value the sine of 2 pi times the phase. Again, the phase is 0 to 1, and we divide that by the harmonic. That gives us our sawtooth wave, and we save that in a temporary table called wavetab dub. And here we maintain a maximum value of the wavetable. So when we've calculated all those double values, which will be between about -1 point something and +1 point something, we go back through that table and we calculate the wavetab dub value by the sample scale, which is 2 to the 15th, 3 to 32,000 and something, and we divide it by the max, and then we save it in the wavetable data. So that gives a wavetable of plus sign maximum to minus sign maximum of a 16-bit signed integer. And then we simply increment the wave data start pointer, so the next table calculated starts at the end of the one we're calculating here. Okay, and also we need to note that although we are using integral samples to create the table, here the sample could be a fractional value, so we can calculate the table value between samples and compare it to the one we interpolate between samples. This allows us to measure the noise we generate when we interpolate using this table. Okay, so we are back in the synthesizer tutorial test program in part 4, obviously, and we are looking here at a function called Sawtable Noise, which assesses the noise for sawtooth tables. And this takes a table size, a maximum harmonic, and an output mode. And what it does, it starts about 40 Hz and increases the pitch gradually until it gets to the point where the maximum harmonic gets to the Nyquist frequency and it stops, because there's no point going on after that. We're just going to get noise we're going to know about. And the output mode at the end here, we can either output the calculated value, the interpolated value, the calculated value being fully floating point calculated. We can output the noise value, which is the difference between those two, and we can output nothing if we don't want to fill our hard disk up with wavetables. So first up, we have 512 table length, we have 64 harmonics, and we're going to look at the calculated output. Okay, let's go. And it now takes a little while because it's doing a lot of floating point calculation and generating quite a long sample, quite a long sound file. Okay, so that's done. So what's the output here? This line gives the maximum MIDI note as nearly 66 and the maximum bass frequency at 367, at which point the maximum harmonic reached the Nyquist frequency, so it stopped generating output. And here it gives the signal and noise in samples and the signal to noise ratio in decibels. So first up, let's see what it's produced there. It's that file. So if we zoom in, we can see it's generated some nice sawtooth wave, and if we play it, it started off quite low, and I'll spare you the whole of it. We'll just play a bit of the high end. Okay, and if we look at the spectral view, we get, as we would expect, a completely clean waveform. There's no noise there. Right, so we shall close that. And we shall go back into here. Now we will generate the interpolated version. Again, I'll spare you sitting waiting for it. Okay, the calculations are exactly the same, it's just the output that's different, so we'll get rid of that and we will go into that one. Okay, and if we'll play some of that. Sanity check, yes. That is a sawtooth wave of increasing frequency. And if we zoom in, we can see it is. However, if we look at the spectral view, we can now see we do have some noise, which we would expect, and that amount of noise was given by the calculations. So, shall we see what that noise is and how it is affected by frequency? So we go back into here and try noise. And off we go again. Okay, so again the same calculation to 50 dB. I'll get rid of that and we will open up the noise and play a bit of that. As we can see, it's independent of frequency, and that's just noise. Fairly horrible stuff. That is amplified quite considerably so we can hear it. And if we look at the spectral view, it's all over the audio spectrum. Okay, so let's investigate how table size and number of harmonics affects the noise. So I'm going to do what we've just done for, as you can see here, we start at table size 256 and go up to 4096. Again, it doubles every time. And for each table size we start at 2 harmonics and then double up the number of harmonics each time, so 2, 4, 8, 16, 32, etc., until we get to half the table size, which is, as we've discussed, the maximum we can go. Shall we see what that brings? Okay, so it started with 256 and harmonics 2 and so on. And this is going to take quite a few minutes, so I shall bring you back when it's done. Okay, done, finally. So I am going to take all these results and put them in a little table and we shall assess what we've got. So now I think we've got to the point where we need to make some decisions which will affect which tables we need to generate. We need to decide the lowest frequency we want the mean green to play, we want to decide the highest frequency we want the mean green to play, and we need to decide the minimum signal to noise ratio we will accept for our oscillator. Let's start with how much noise we will accept. To recap, we generate a table to be used for one note or a group of notes. When we generate tables for a note, we know we want the maximum harmonic in the table to be at 12 kHz for that note, an octave below the Nyquist frequency. We can thus obtain the maximum harmonic we want for the table by dividing the frequency of the note into 1200. So looking at the table here, if we know the maximum number of harmonics we want to generate and we know the noise performance we want to achieve, we can pretty much look up the table size we need to use. Okay, I've looked at this table and as a result I've taken an executive decision that we will aim for at least 60 dB signal to noise ratio. Having made this decision, we can see that we need to be in this region here. As a result of this, I ran the test program again for each table size, looking for the maximum harmonic that fell within our noise limit. This took some time to run and the results were as follows. Now what about note range? Well, soundprogramming.net helpfully give us the MIDI note number ranges of a range of instruments. So let us set our lowest note at 28, the lowest note of a bass guitar, and our highest note at 102, the highest note of a piccolo. These correspond to frequencies of 41 and 2960 Hz. When we generate tables for these notes, we know we want the maximum harmonic to be 12 kHz, as we've discussed. So we can simply obtain it by dividing the frequency into 1200, which gives 291 harmonics for the low note and 4 harmonics for the high note. Looking back again at our table we obtained for how many harmonics we can get within our noise specification, we see that we have to use a table of 4096 samples, as this is the only one we've considered that gives us a maximum harmonic of 291 or greater. Okay, we've looked at the Wavetable generate table function, which generates one table given max harmonic size and the start of the storage for that table. So this function decides what tables to generate and calls that function to generate them. So what we do, because we pick a table depending on the MIDI note at the start of the note, we make a list of 128 table start positions, one for each note, and they're not all different tables, as we'll see. Okay, we just said that the mean green is going to operate between MIDI notes 28 and 102, but we're going to point to a table for all the MIDI notes 0 to 127, and beyond those ranges the performance might drop off a little, but at least it'll do something. So we have our note number here, and here we calculate a frequency in Hertz for that note number, and the next line down we calculate our max harmonic, which is sample rate over 4, 12,000 over the frequency. Now these two lines just make sure that the maximum harmonic for the table we're going to calculate is within the range we said, which is 4 to 300. Okay, so now we want to decide whether we actually need to generate another table here. We're hoping to use one wavetable per semitone, but as was in the case with the Dark Star, we might not be able to. So that's what this does. Wavetable note step is the number of notes we step on before we generate a new table, and hopefully one, but we will try it for a different value. And here at higher notes we find we actually don't need one wavetable per note, so that's what this is doing. It's just checking whether the max harmonic value was the same as the last one, in which case we've already got the table, so we don't need to generate a new table. And right at the bottom here we just print out the total size of memory we've used for our wavetables. just to check we're not using too much. So shall we run it and see what happens? Okay, so the first thing we notice is table size 512 kilobytes. So as it is, we'd be using the whole of the flash memory in the chip just for storing wavetables. So we have a problem here. And just to scan back through here, if we go to the bottom, yes, from MIDI note 0 to MIDI note 27, it uses the same table. And as the number of harmonics gets down into the teens, we find one table will do for more than one note, and we've said 4 is the minimum we're going to go to. So if we go in here and set step, this is the note step for the tables. If we set that to 4, we should get 3 tables an octave. So let's see how that does, whether that brings our flash ROM usage down to an acceptable level. Okay, yes, table size down to 160 kilobyte, which is still somewhat more than I was hoping for. I was hoping near 100 kilobytes. But if we do look up here, we can see, so 60 is a table. There's a table at note 60, there's another table at 64, another table at 68. So 3 tables an octave. So that's worked. But that's not the direction I wanted to go in, so I am now going to investigate using variable length tables. That is, when we want fewer harmonics, we use a shorter table. Okay, so I've converted the table generation to generate tables the size of which depends on the number of harmonics. The first change is the list of table start positions for each MIDI note, which is now a structure, not just a single value, which contains the table start and now the table size and mask and shift values, which we will look at in more detail when we come to look at the operation of the oscillator. Okay, so here we're back in the Wavetable generate all function, and the changes are down here when we come to actually generate a table. First thing we need to do is get the wavetable size from the maximum harmonic we want, and here is the function that does it, get wavetable size, which gets a wavetable size according to this table we calculated earlier. And remember, the values in the table there are the maximum harmonic content we can have for that particular table size. So we actually need to use the bigger table to make sure we can have the harmonic content we like. And remember, in this table, this is the maximum harmonic number we can have for that table size to give our 60 dB signal to noise. So we want at least that signal to noise, so we always want the bigger table than that. Okay, so we've got our table size, so we call the set wavetable note select function just to set the table information, specifically start and size, for that particular MIDI note, and then we just generate the table as we did before. So shall we see what it does? Okay, generating a bunch of tables, and it's 187k, which is still a bit more than I wanted, but getting close. And we can see here now where it says new, it gives the table size for the table it's generating. So I think I might go with that for now. But if we do start running out of flash on the STM32, we could go down to a step of 2, and we'll run that one. Which takes us down to 100k, which was what I was aiming at, and you can see it's generating a table for every other semitone here. Now I think we have our tables, so let's go and build our oscillator.
Well, at this point I think I owe an apology. I promised an oscillator and all I delivered was wavetables, and it's felt like pretty hard going to get this far, so I'm gonna wrap it up here on this video. However, that is the thing with digital audio, you have to get it right. If you don't, you'll get digital noise in your signal and it'll sound digital, so it's just one of those things. So next time we'll wrap up the oscillator. We'll figure out how we're going to convert pitch to frequency without using floating point powers, which is what we're doing at the minute. We'll build the oscillator, we'll test the oscillator, and we'll get the square pulse waveform generated, because thus far we've only considered sawtooth waveforms. So that's it for this one. I look forward to seeing you on the next one. Until then, it's goodbye from Tripplikit. Goodbye.